talking about collaborative causal discovery with atomic interventions. The time is all yours.
Thank you, Chris. I also want to thank the organizers, Leonard and Raghu, for inviting me. My name is Shiva Kashishnath. The title of the talk is Collaborative Causal Discovery with Atomic Interventions. And this is joining to work with Raghav, who's also in the audience and also on the job market. So if you have any positions, contact him. I guess the main part of this talk is to introduce a new model for causal discovery where we want to learn multiple causal graphs together, and I think motivating the model is going to be the main part of this talk. So let me start with the basic problem of causal discovery, where we have a set of variables and we want to understand the causal relationships that between these variables, right? So we have some sort of 5 variables in this graphs, and then we want to understand which variables is causing which, right? I mean, the cause effect relationship of between these variables. So that's the basic problem of causal discovery. But I think the question that we started with is there one universal causal graph, right? I mean, in multiple scenarios, that's not the case, right? So in many practical examples, if you take, there is no really one universal causal graph that describes your entire relationship between the variables. The causal graph itself could change over time, could change between people, could change between populations, and so on, right? And this is true if you look at sciences. There are a lot of publications which explain this phenomena, where they explain that there is not really one underlying causal graph, but there is really multiple causal graphs. And in this case, I'm going to define a causal graph which also has latents. So the variables could be the same, but the latents could also be different, right? For example, this is there's a paper that we took from on in epidemiology about talking about incidence of diabetes, which is a target variable. So they explained about like different latent variables that could come. I mean, and the latent variables could have different influences, right? So the causal graph defined on the observable plus the latents could be different for different set of populations, right? So subpopulation 1 would have a causal graph where economic status is influencing the variables, physical activity and diet. Maybe there's a culture of drinking more alcohol, and that could have an incidence on that, could have an effect on this, and there could also genetic reasons, and there could be some combination of these also. So, I mean, I guess in causal discovery, we already have a hard problem. There've been lots of exciting work in the last decade or so, but about in causal discovery with intervention design, without intervention design. But I think we try to learn something higher here, where we said that how about we learn all these causal graphs, right? Instead of learning one causal graph, can we learn all of them together? And can we use some kind of structural assumptions or collaboration between these different entities that are there to make the problem somewhat easier?
A quick clarification question.
Yes.
Just, since you refer to these as subpopulations, is there a difference between this setup and just thinking this is a mixture of different graphs?
I mean, that's one way of modeling it. I mean, this would be a slightly different way of modeling it. I mean, that's another line of modeling which we should take as that's a mixture of these subpopulations and learning them. Yes.
Also clarification. But the graphs are the same. The
observables are going to be the same, but the latents are not going to be the same. Okay, so we are thinking of like a modeling question where we have the same set of observables across different entities or populations, but they're going to be the latents could be different, right? So the overall graph is not going to be the same, but the set of observables are the same.
I guess maybe one more clarification. Are we assuming that there's like in all 3 of these subpopulations, there's the 3 latent variables, but in the first one, culture and genes don't have any effect? In the second
this is just an example, but yes, no, there's no really restriction on that. They could be there. Yeah, I just put an example there. Okay, so let me just again rephrase what we've been saying so far. So we have say n entities, and the entities could be individuals when we're thinking of like individual experiments or collection of individuals, and each of them we believe has their own causal graph, which could be same or be different. I mean, there's no reason for them to be different, but they could also be the same, but they could be different too, right? I mean, again, this notion of entities, something like in other contexts, could be businesses or medical agencies who want to collaborate to learn something together, right? I mean, they could be like companies who are working together to learn to better understand their process, or could be medical agencies who could be collaborating with each other, hospitals, for example. And each of them might have their own causal graphs, which could again be same or different. We're not going to say anything about that for now, but we could say that they have n causal graphs, and the goal is to learn them all together, right? Okay. So yeah, so the goal is that to learn all these causal graphs of these entities, assuming access to their individual data. So I guess one of the definition of entity is important here. So we are going to say that an entity is on the same set of observable answering Frederick's question, and basically, and maybe also this, each of them generates their own data, right? So entity is a population or a hospital or a business who's generating their own data, right? And so that we can have access to their data. and we can do things with that data, like do experiments or get observational data. Okay, so now just a 2-minute detour. This might be not be useful for this audience, but let's just understand how, so that we are on the same page. How do we learn a causal graph? And this is a standard question in causal discovery. Is that like the first observation is that like the observational data itself is not sufficient because you can't learn exactly the causal relationship. You can only learn within a Markov equivalence class. And if you want to distinguish more within an equivalence class, you need to do something more. And the notion of interventions or experiments come into the picture at that point. Like you do interventions or experiments that helps you distinguish within a Markov equivalence class. Okay, right. For example, on this case, you can do an experiment or intervention on, and in this case, I'm going to talk about do interventions introduced by Pearl. So basically, like say if you're intervening on a variable called say diet, so you can fix a diet to a low or high value and do your randomized experiments or something, and then you can understand the effect of that, and that can be used for causal discovery, right? I mean, so you make some more assumptions like faithfulness, and then you can go from interventions to back to the graph. So basically, the effect of an intervention is that all the incoming edges onto the variable disappears, and this is graphically what happens when you do intervention on a variable. Okay, so there is a lot of recent exciting work in this area of how to do efficient intervention design for causal discovery, but much of this work has been focused on this large intervention set, right? I mean, I think in a way this is somewhat necessary. Like there is no way to avoid it. In fact, we have a recent result which shows that if you have latents, then you need at least an intervention set that is linear in the size of the variables. So there is no way to avoid that if you have latents in the system. So in a way that's unavoidable. So if you want to discover the causal graph exactly, you need a large intervention set. Okay, so but the problem is that these in practice the large interventions are infeasible, right? So like imagine that you want to do intervention on 3 variables together, physical activity, alcohol, diet. I mean that might be hard for somebody to do it, right? I mean it's just a hard design experiment to construct when you want to intervene on multiple variables together. Okay, so in this work we kind of said, okay, so basically what can we do, right? I mean, so we need big interventions, a large set of interventions, but we can't do it in practice. So in this talk, I'm going to just focus on atomic interventions, which is basically intervening on a single variable. Okay, so you're going to intervene, but you're going to intervene on a single variable at a time. Okay, so then, as I said, learning the exact causal DAG is not possible in this. I mean, there are lower bounds that rule this out. So the question is, what else can we do, right? So I mean, we can't learn the exact causal DAG. I mean, so maybe some other structure can we learn. And in fact, there is a nice structure that comes in that's already been there in the literature for a while, called Maximal Ancestral Graphs, which can be learned using single variable interventions. And so, I mean, just an introduction in Max. So Max are types of causal graphs which encode higher order relationships. So they encode like ancestral relationships. That's the name ancestral graphs coming from. And they also encode the presence of latents. Like I mean, there are not only directed edges now, but there is something called as bidirected edges, and that is used to encode latents. Yeah, and it's not hard, but we show that we can recover max using just single variable interventions. Okay, so I'm not going to explain how to construct a DAG from a mag, but for what I'm going to say is that like I'm just going to explain what the meaning of edges in a mag is, so that we are on this. So basically, we have the directed edges, which are like the standard directed edges, but now they have a slightly different meaning. So an edge from A to B doesn't mean that A is a parent of B. It just means that A is ancestor of B and B is not ancestor of A. I mean, and it doesn't rule out the possible of latent confounding between A and B. And the bidirected edge basically means that A is not ancestor of B and B is not ancestor of A, and A and B are confounded. So it's kind of a representation. You can think of a graph where you have observables and latents, and now you're constructing a graph only on observables, but you're adding these kind of directed and bidirected edges. And there is a nice construction that every DAG with latents can be transformed into unique mag with observed variables. There's easy construction to do that. And again, if you don't want to think of mags, I mean, you can think about a situation without latents, and then under causal sufficiency, mags and DAGs are the same. So only in the presence of latents do they differ. Otherwise, they are just the same. Okay, so then this is a long line of work in investigating mags, and many people in this program have contributed to this work. So I mean, so I just want to give some like a brief overview of what mags were, and like introduced by Richardson as splits in 2002. And this is like there is at most one edge between a pair of vertices. The edge could be directed or bidirected, right? And so one of the nice properties is that it's closed under marginalization and conditioning, and which normal DAGs don't, right? So basically what it means is that like if you take a distribution and that is faithful for a DAG, and if I do marginalize on some variables, the resulting distribution may not be representing any DAG. So that's so that's for the DAGs, that's not happening. For MAGs, that will always happen, right? So if you do marginalize over the distributions or condition over the distributions, you are still getting in the MAG world. So that's a nice property that MAGs have, which DAGs don't have. And I think that there is also this nice literature on causal reasoning, what you can do with these MAGs. And you can do, there is a notion of do calculus extended to these MAGs. There are notions of D separation, which are extended to M separation. And there's entire literature on work on like explaining how these things work out. And in this case, like the Markov equivalence class is called partial ancestral graph. And like if you're known about, like you might have known about this algorithm called FCI, which is a very popular algorithm in causal discovery. And it actually, what it does is that it actually generates a partial ancestral graph from observational data. So if you run FCI, if you're seeing FCI, that's basically what it's doing. It's generating a partial ancestral graph. Okay, so I guess so the revised goal that we're going to focus now is that we are going to learn MAGs. Okay, so we are not going to learn the causal DAGs, which are impossible with atomic interventions. We are going to assume that can we learn the MAGs? Can we learn the MAGs of the entities, assuming access to individual data? Yeah. And a natural objective to think is that like now we have interventions, we want to minimize the number of interventions, right? So you have entities that are doing interventions, you want to minimize the maximum number of intervention any entity does. So any questions so far? Yes.
So it's one bag from observational data which related to lots of DAGs. I mean, from given one MAG, it can map into.
Yes, yeah. So the mapping from DAG to MAG is unique, the MAG to DAG is not, right? So the lot of yeah. If you consider a unique MAG from a DAG, but the other way is not true. Okay, so I guess the key punchline in this work is that if you have entities and if they can somehow collaborate with each other, the problem actually becomes much easier. That's kind of the main takeaway that we're going to explore. And how do we formally show this is that we assume some kind of underlying structure or clustering of these entities based on their max. So because I'm going to define a natural notion of clustering, which comes in, like if you worked in theoretical CS, like these notion of clustering comes quite often in a lot of different areas. But like for this, let me explain what this clustering is here. For example, what we're going to assume is that the entities have some clustering. So there's a clustering of these entities. So there are entities, I'm going to cluster them. There's some underlying clustering, which is unknown for us, but we assume that's there. Okay, so basically the idea is that any two entities belonging to different clusters have their max are some far apart, and any two entities in the same cluster have close by max. Okay, so I have to define what a close by and far apart means, but this is the rough idea, right? So we assume that there is some ground truth clustering in the universe that these entities satisfy, and so that within the cluster the distances are small, and across cluster the distances are big. Okay, so let me a little bit more formal with this model, and so let's say the MI denote the mag associated with entity I, and let's say n is the number of variables. We are going to define a distance between two mags as the number of nodes with different neighborhoods. So we are going to assume that like the difference between two mags, the distance between two mags is the number of nodes on which they have different neighborhood, right? So for example, in this case, I'm just a very simple example. So basically I have these two mags are same except for this bidirected edge. So they differ in the neighborhoods of A and C would change between MI and MJ. So the distance is basically 2. So I'm just measuring the number of nodes with different neighborhoods, and that's my distance between the mags. Again, one could think of other notions of distances, and but this is the notion that we work with. Yes.
This is a silly question, but does this define like an actual?
It's symmetric, yeah. It's symmetric.
Awesome.
Yeah. So now from there, so now once you have a distance notion, now we can be more formal in defining what is far away and closer. So I'm going to say that the mags M1 to M1 are belonging to the entity, and there exists a clustering, a ground truth clustering, C1 star to CK star, and these entities satisfy alpha beta clustering if any entities in the same cluster have distance at most beta n apart, and if you have two entities in a different cluster, they're at least alpha n apart. So there is a separation between entities within the same cluster and different clusters. So if they're in the same cluster, there is some they're close by, and entities within between across clusters are far.
What is little n here?
The n is the number of variables in the observable variables. Yeah, the n denotes number of observables. Yeah. Let's assume the same. It's a set of variables are the same as the set.
So beta is in between 0 and
The beta would be 0. Yeah. Yeah, we would explain one of the cases would be where the beta is 0. Yeah, and like you say, there's no restriction on k in general. So basically, this is not any set of max. Given any set of max, I can have an alpha and beta which is satisfied. So that's not. So this is not a restriction on the model. It's just like that. I mean, we ideally would like to think of alpha as beta as constants in practice, right? I mean, that would be the nice case because our results might change with alpha and betas, but this will capture all the max, right? We can just set alpha and beta in any how. Right? So we can always put an entity in a different cluster. Okay, so let me just quickly say that, like, so let's say here we have 7 entities, and so this would be a max with alpha 0.75 and beta 0.5. So let me just quickly show one example. So for example, if you take any two max, you can see that they only differ in 2 nodes, in this case A and D. So that's beta is 2. There are different 2 neighborhoods. So and the number of nodes is 4. So beta is 2.5. And like if you take any 2 entities which are in different clusters, they differ in at least 3 nodes neighborhoods. So A, C, D. So the alpha is 3 by 4, which is 0.75. Okay, so these clusterings can be, so for there exists an alpha beta value so that any set of M max would satisfy this notion. Okay, so now let me quickly go to the results. So what we show is that if you make these, if you're under these assumptions of this model being there exists an alpha beta value so that your entities satisfy this alpha beta clustering, what we show is that we have algorithms that now depend on alpha and beta. So just to give a baseline, so if entities don't collaborate but they learn independently of each other, then you can learn with n atomic interventions, but you also need an n atomic interventions. We show a low bound there too, showing that if you don't collaborate, if each of them operates independently, you need at least n atomic interventions to learn a bag. So there's that's the when you don't collaborate, but if entities can share some information across them, then you can reduce like these bounds to something that now only depend on alpha and beta and log dependence on n and k. And we also have our lower bounds, which shows like at least in some regimes these like this 1 by alpha dependence is unavoidable, right? So there exists no algorithms which would be able to learn these without these many interventions. Okay, so that's kind of the rough idea. And here delta is the maximum degree across all the max. Right. So yeah. So and as you were asking, so there are stronger results under alpha 0. So when beta is 0. So when beta is 0 means that all the entities in the same cluster have the same max. That is basically the beta 0 case. So there are stronger results when you have beta equal to 0. Right. So yeah. So that's when beta 0, each cluster is representing the same max. Okay, so basically, let me quickly give an overview of an approach. So algorithms work in 2 stages. I mean, this is kind of the natural way one would think about these problems if you know these modeling. If you assume these models, for example, the phase 1 is to recover the cluster memberships, right? I mean, so we assume there is a ground truth clustering, which we don't know, but the first phase would be to recover these cluster memberships, and then we use these cluster memberships, and from clusters we go to the max. Okay, so I think the idea is quite simple actually once you think about it a little bit. So what we do is we sample a set of observable nodes and intervene on them for each of the entities. So we are going to take some set of nodes that we ask everybody to intervene on that, and that would construct a partial mag on each of these entities. So these are not really the mags, but these are not really the pags. It's something in between because now we have done some interventions. So we know some edges correctly, but many of the edges we still don't know. And you're going to use that to recover the clusters using these partial neighborhood information. And then we are going to once we recover the clusters, the idea is to somehow load balance the interventions across everybody in the cluster. So you first recover the clusters, and now you have the clusters. Now what you can do is, okay, now have like these entities. I know they are all somehow related, so I can somehow load balance, and from that I learn the max. Okay, so that's kind of the, so let me just like explain quickly. So yeah, so we have a set of variables that we want to, so you can start with like partial ancestor graphs, which we know how to obtain using an FCI or some other algorithm. So let's say that that's given. I mean, we don't need that, but we can start from there. And so we sample a set of random nodes, and we just intervene on nodes, on those nodes and all their neighbors. So this is assuming that you intervene on nodes and their neighbors. Okay, so what we construct is a partial mag. So again, this is something that's in between a PAG and a mag, because it's not it has more information than a PAG, but it's not the true mag. Okay, so the idea is that like this is a very simple observation to make, that if you have an undirected edge and if you intervene on A, so you have two kinds of things that could learn from. If A is dependent on B under intervention, then you can show that this is A, the direction of edges has to be like this. But if A is independent of B under do of A, you actually need to do one more test. Right? You also have to intervene on B, and that's that. And if that is also independent, then you can say A and B are bidirected edge. So that's why I guess maybe that's why we don't only have to intervene on S, we also have to intervene on their neighbors. That's why we don't intervene on S alone, we also intervene on the neighbors of S. So we have to learn, this test requires intervening on both A and B when you have independence. Okay, and again, I guess the idea is that once you construct these partial neighborhoods, we just do a natural clustering on them, and then we show that I mean, I'm just going to talk about alpha zero clustering, but it also happens in the alpha beta case, that with high probability you can recover these clusters. So these are Monte Carlo algorithms. That means that like the assumptions that like we are going to succeed with high probability, right? I mean, with high probability, I'm going to get the true clustering back.
Probabilities over the sampling.
Probability is over sampling, yeah. The probability is sampling. That's the only probability. There is no assumptions on the max. Okay, and now I guess there's a more complicated way. I mean, like in this case, what I did was intervene on S and all the neighbors on S. So that will give me that depends on the maximum degree if you look at this. But there is a more complicated way of removing this dependence on this max degree, and which is a more complicated algorithm. And these ideas also extend to alpha beta clustering, like where what happens is that within the cluster, the max are not the same. There's already some variation between the max within the single cluster even. Okay, so that's what I'm going to say about the upper bounds. How many minutes there?
You have in between 5 and 10, start a little bit late, so 8.
Okay, I think I'll be done. Yeah, so okay, so yeah. Okay, great. So what about the low bound? I mean, so yeah, before that, let me ask, is there any questions? Other question?
Just, so if I ignore line 1 there about the related dependence, I did have a question on maximum degree. So the maximum degree is of the mag.
Undirected, yeah, the undirected. Yeah, so basically you look at the skeletons among all the mags in the class. Yeah.
And I want to understand how that depends upon possibly upon the original degree of some DAG that kind of created that mag.
Yeah, it's a great question. I think like if I mean obviously like with the latents it could be arbitrary.
If I have just a Harvard chain, because can it blow up if I have a long chain?
It can blow up, right? If it's a long chain, there could be edges that go all the way. Yeah, it could blow up. Yeah. So this is in terms of max, the maximum degree in terms of mag, but there's not really an easy way to describe it.
So you want the original DAG not to have had long chains in it?
Right. Yeah, I mean, if the goal is like, yeah, I mean, in this case, I guess we are thinking of only about mags and everything is happening in the mag world. But if you're thinking in the DAG world, you probably want some kind of some restriction on the DAGs that would make sure the maximum degree in the max is not high, and that would lead to that. But we have an algorithm that doesn't depend on maximum degree, but you're right. That like in the long chain, they will blow up. At least the first node would have paths to all the nodes that follow it.
Question. Does it, these lower bounds that you mentioned, they should also depend on the degree of the latents, right? If that's bounded, then you probably only need like bounded interventions.
There is probably a more refined version, which would like, I mean, I guess these low bounds are going to just say about like in the max, I mean, how many interventions, assuming the clustering.
I meant the original ones when you said it was impossible to or something.
Yes, so those low ones, yeah. So there is no restriction on the latency. Yes, but yeah, you're right. Like if you assume there could be only be like say k latents, then there's a bound that would depend
Or
on k.
degree
But
k or something.
yeah, exactly. Right.
Yeah,
So,
I think
so actually, no, it's number of latents that matter. Like
Yeah.
we are like those low bounds also hold when each latent is only affecting two variables, so it's a semi-Markovian case. But its number of latents would play. Like if you assume that only k pair of variables would be affected by the latents, then the low bound would be much weaker.
And remind me again of the significance of like atomic interventions. Like what is the
I think they come in practice. Like I think that's one of the main motivations, because in practice you can't do interventions on that set of variables because there's one reason that it's impossible to design an experiment. The second reason is also like when you do these kind of conditional independence tests, then you're like let's even say you have k variables, so you're intervening one together, your domain size is not 2 to the power k, even if the variables are binary. So you're doing every pair of like 2 to the power k, right? You're setting a variable to just 0, 1, 0, 1, so on. So multiple reasons why to avoid like interventions.
Mostly to avoid like data like sparsity.
Yeah, you need a large amount of data to make any reasonable inference in that case. Yes. Oh, sorry. Yeah.
I'm just letting you know.
Oh, okay. Okay. Yeah. So I think so. Just a word about low bounds. I think maybe that's interesting. I mean, so basically, in this case again, we are only leaving the man words, and we're going to talk about this man word, and maybe there's some translation to the DAG world, but that's not done here. So what we do is we consider the distribution over these max and show that every deterministic algorithm would require omega 1 by alpha interventions, and then there is this famous theorem by Zhao, which talks about how to take average case guarantees on deterministic algorithms and translate into worst case guarantees on randomized algorithms, and that basically would we use that directly, and that would give us this lower bound, which says that any randomized algorithm would not be able to succeed without at least omega 1 by interventions. So basically, this is the hard work, and this just follows directly from the Zhao's theorem. So basically, what we are saying is that like no matter what algorithm you design, if you want to succeed with any reasonable probability, where reasonable this means like say 3/4, you would need at least these many interventions. So any questions there? Sorry.
Wait, is your algorithm also recovered after the cluster membership? Did you show this?
Yeah, we do recover that. Yeah, we do recover. Yeah, so there is a phase 2 which would go from cluster memberships to the cluster max.
And a similar complexity, or?
Yeah, I mean, I think the idea is actually kind of natural, right? Once you know what happens within the entity, in the clusters, then you can kind of know how to balance the load, right? You know, they are somewhat similar, like, and then you can say, okay, how to design now these interventions so that they are going to be somehow balanced, right? The goal is to minimize the maximum number of interventions, right? So it's best to spread them across everybody, right? And then learn the information and then share it, right? That's the natural idea. Okay, so yeah, I guess we also ran this in experiments, and I guess these are just for cluster memberships. But what we show is that like even in practice, like we need like you can reduce the number of interventions. As I said, a trivial bound is the number of variables, but we can do much smaller than that, like at least half. Like these are small data sets, like small set of variables, but even there we're saying that like with like even 5 variables we can get like the exact mag recovery under this alpha clustering. Okay, so let me just conclude. I'm running out of time. So I think the main contribution is that we introduce in our new causal discovery model to capture practical scenarios, which includes multiple causal graphs. So we believe that that's what happens in practice, right? There is no really one causal graph that explains everything. There's really a set of causal graphs, and that's what we want to learn all of them somehow. And basically we show that under some natural clustering assumptions, we show that we can learn with a few number of interventions than learning them individually. And yeah, I guess I'm going to talk about so one of the open directions is that like these algorithms are non-adaptive. So basically having some kind of these algorithms are adaptive. So we want non-adaptive algorithms that can be run in parallel. So basically what happens is that like if you want to do, if you have non-adaptive algorithms, you can run them in parallel. Otherwise you have to run them one after the other because you can't, like, you have to wait for one intervention to finish before you start the intervention. I'm going to end here, so out of time. So yeah, happy to take any questions. Thank you.
And if there are any, we can have like one question here, and then we'll be on break. Any questions? Yes.
I'm just wondering about the non-collaborative setting. So imagine you have basically the exact same setup, but the agents say they're like businesses. They're not going to share data with each other. Is there anything that can be said in that setting?
Yeah, I mean, I guess not. I mean, in this case, we don't share it. They don't share data, right? I mean, we are not pooling the data. Like each of them does interventions, and they're just sharing the graphical information, right? You're only sharing we're not sharing them together. We are not pooling the data together. So we're only sharing the fact that, yeah, in your case, yeah, A is causing B. So maybe that's true for me too, right? Because there's a reason to believe that we are same. Right? So maybe that's okay to share again. But if you can't even share that, then I'm not sure what.
Great. Let's take a Eva. We'll go on break, and we'll be back at 3:30.